Hello everyone, and welcome back to my channel. Today we'll be starting a new mini-series on the classical chemistry experiments that give us so much of what we know today. In this video, I'll be talking about the Rutherford gold foil experiment, which was revolutionary in the development of our current model of the atom. And just to give a quick overview, we're first going to go over some of the context for this experiment, then the setup and the theoretical basis behind it. Then we'll talk about the results, what he found, and the further developments since then that have characterized how we view the atom. So, to begin, let's take a quick look at what scientists thought the atom looked like before Rutherford's crucial experiment. The previous atomic model was Thomson's plum pudding model, which I've sketched out here. They imagined the atom a bit like a bowl of pudding. In this case, the pudding itself is positively charged. So there was no concept of a positively charged particle like the proton that we have today. They did have something similar to the electron though, based on some of Thomson's cathode ray experiments. They thought there were negative charges, which they called corpuscles, that were embedded like pieces of plum throughout the pudding or the atom. But beyond that, they didn't really have any ideas on any more detailed level of organization. The negative charges were thought to be placed pretty randomly throughout the atom, and there was no empty space in the model. So everything is either this positive pudding or these negative plums. And they also didn't have a concept of a neutral third particle, which we would today know as the neutron. That's kind of our starting point here. And what Rutherford really wanted to figure out was if there was any more order to this structure. So for instance, was the positive charge really a pudding-like substance, or was it more localized to particular parts of the atom? Or perhaps, how much space did this positive part of the atom actually take up relative to these negative parts of the atom that Rutherford had characterized? So, Rutherford tests all this stuff with his gold foil experiment. To basically summarize it, he shot alpha particles, which are these red guys here, out of a radioactive alpha particle emitter at an ultra-thin sheet of gold foil, just a couple of atoms thick. And he had a 360-degree detector that would display exactly where each alpha particle ended up after making contact with the gold foil. But what is an alpha particle, and why would Rutherford want to use them? So it's actually just a particle made up of 2 protons and 2 neutrons, with no electrons, meaning it's got a positive 2 charge overall. You can also think of it as the nucleus of a helium atom that's been stripped of all its electrons. He used them because they're very easy to generate via radioactive decay, hence this radioactive alpha particle generator, and because they have positive charge. So Rutherford knew that positive charges would repel each other, so he suspected that whenever the alpha particle made contact with a positively charged area of the gold foil or a positively charged area of the gold atom, it would deflect in some way off of the sheet instead of just going straight through because of that positive repulsion. And when the particle made contact with a negatively charged area of the sheet, they should attract each other, sending the alpha particle straight through. So, what happened? Well, the vast majority of the alpha particles that Rutherford shot at the foil either went straight through with absolutely no deflection at all, or were just minimally deflected, and just a very small proportion of the particles actually deflected backwards, so towards his radioactive emitter. So to explain this, let's look at how an alpha particle would interact with either a negatively charged part of the atom or a positively charged part of the atom, which we know today as the nucleus, the gold nucleus. So electrons are tiny compared to the alpha particle, and they're basically massless, and they're negatively charged, which would attract the alpha particle and allow it to essentially punch right through them. Because remember, alpha particles are really, really big compared to electrons, so it kind of just pass right through them, especially since they're oppositely charged. However, if the alpha particle encounters a gold nucleus, which is both positively charged and much more massive than it, we would expect the particle to deflect backwards because it couldn't punch right through that giant gold nucleus, and they repel each other. So let's summarize the results and Rutherford's conclusions from them. So first, again, he observed that most alpha particles went straight through the gold foil sheet or were just barely deflected. And very few alpha particles were deflected backwards towards the radioactive emitter. And he also knew that alpha particles should go through regions populated by electrons and deflect or bounce off of gold nuclei. So from all of these observations and facts, he concludes that most of the atom space must be taken up either by negative charges, which he might have called corpuscles, but electrons as we do them today, or completely empty space, because the alpha particles would also presumably pass through empty space. And he also concluded that the majority of the mass of the atom and the positive charge would be concentrated in a very small area, which we know today as the nucleus. And so if we sketch this out, we get a model of the atom after Rutherford's discovery. There's a small, massive, and positively charged region, which I'm going to arbitrarily put at the center of the atom because that kind of just makes sense intuitively. And it's surrounded by a large negatively charged space, which contains electrons and contains very little mass by comparison with the positively charged region, the nucleus. That's basically all for that. But just to give a quick preview of what sort of happens next in the history of science, in the early 1900s, physicists discovered a phenomenon called energy quantization. And here, all that means is that energy exists in distinct quantities or levels. And therefore, each particle can only have a certain limited set of values for their energy. So, maybe if I'm an electron, I'm only allowed to have 1, 2, 4, 6, or 10 units of energy, whatever that means. And the implication here, combined with the Rutherford model, creates what we end up knowing as the Bohr model of the atom, where electrons are separated into these shells that I'm sure you've seen before, based on their energy level. And you can't have an electron in between the shells because electrons can only have certain precise values for their energies. So that is all for today. If you're interested in private tutoring, like the way I teach, you can send me an email. I'll drop that right below. lucassius5@gmail. And see you next time.